Welcome, everybody. My name is Kumar Murthy. I'm the director of the Fields Institute. And normally when programs begin, it's the pleasant duty of either the director or the deputy director to welcome all the participants. Today, I want to take a moment to make a few additional remarks. Some of you may be familiar with them, others from different parts of the world you may not know, but September 30th is the National Day for Truth and Reconciliation. It's part of the process in Canada that we're going through of dealing with the colonial past. And this day has been established to honor the lost children and survivors of residential schools while acknowledging the enduring pain and loss suffered by their families and communities. So all over the various events are being planned for observing this National Day. Public commemoration of the tragic history and ongoing impacts of residential schools is a vital component of the reconciliation process. And as such, we wish to acknowledge the lasting harm that was caused by the 140 federally run Indian residential schools which operated in Canada between 1831 and 1998. First Nations, Inuit, and Métis peoples have rich and diverse cultures, voices, experience, and stories, and I encourage you to explore them. There are a number of online resources that can provide a deeper historical and contextual understanding of our role in the past and what we can do to create a better future together. Reconciliation Canada is an Indigenous-led website that has aggregated numerous links that provide a good breadth of resources. And if you're so inclined, I also encourage you to explore the work of Indigenous mathematicians across the country, many of whom have made important contributions to the field. University of British Columbia in particular has put together a robust network of Indigenous math resources for the classroom and the community. Now you've gathered together today for the Fields Center for Financial Industries Bootcamp on Machine Learning for Quantitative Finance. I'm sure you're going to find it very engaging and useful. Many of you perhaps are repeat visitors. Some of you may be new. So for those that are new, let me just say a few words about the Fields Institute. The main theme of the Institute is to encourage, promote, and facilitate research and training in the mathematical sciences. We are a network of 20 universities, so we are quite a broad group of academics. We're funded by the federal and the provincial governments, by the National Science Foundation, the Simons Foundation, and also by generous individual donors. The program you're going to engage in today is going to be intense, but I think very, very rewarding. You've got excellent people organizing and running the program. And I think you will find that there's a lot here to wrap your minds around. So I hope it enables you to take advantage of the many opportunities, both in research and applications. And I wish you, all participants, wherever you're connecting from, all the best in this workshop. So now I hand it over to the very capable hands of your organizers. Maybe Sebastian, you're next.
Okay, thank you very much, Kumar, for the opening remarks. And welcome everyone to our Fields-CFI Bootcamp on Machine Learning for Quantitative Finance. I also want to thank our sponsors through the Center for Financial Industries, Scotiabank, for their continual support through the years, and our former sponsors, TMX, as well as, TMX and Sun Life. Today's bootcamp is kicking off with a tutorial session by Professor Ruimeng Q. And Ruimeng is an assistant professor at the University of California, Santa Barbara, with a joint appointment in mathematics and statistics and applied probability. And before that, she was at Columbia University as a term assistant professor. Her current research interests are quite varied, and they lie in the interdisciplinary area of machine learning, financial mathematics, and game theory. She's supported by NSF Grant and Faculty Career Award at UCSB. And this morning, Ruimeng, I guess perhaps you can try sharing your screen. We should have actually tested that a moment ago, but let's do that now. And while you're doing that, I'd like to say that I'm sharing this session on behalf of my organizing committee, Matt Davison, Dan Rosen, and David Saunders, who I think most of them are all here. David, I believe, is teaching. So it seems to be coming up.
Yeah, I'm trying to share my screen. Can you see it?
Okay, great. We can see your screen. Okay. And your title hasn't changed, it looks like, or has it?
No.
No, good. Okay, yeah. So it's Introduction to Deep Learning with Application Stochastic Control in Games. So Ruimeng, the pleasure is ours, and floor is yours.
Oh, thank you. Thank you, Sebastian, for this nice introduction. And also, I'm very happy to be here and give this tutorial session. Today, I will be briefly review the main neural network architecture that has been used to deal with stochastic control problems and games. Those are the well-known feed-forward neural networks, and then also the recurrent neural networks, in particular the long short-term memory networks. And then I will be talking about different ways to tackle the control problems and the games. Okay.
Ruimeng, one small, I forgot one small administrative aspect, and that's how you would like to address questions. Would you like individuals to interrupt you as we go along,
Sure.
or wait until the end?
Yeah, I prefer to have like more interactions if there are questions in the middle. Yeah.
So
yeah,
those who are attending, I prefer if you type in your question, and then I will interrupt Ruimeng at an appropriate time shortly after that for you then to ask. Sounds good?
Oh, sounds good. Yeah, thank you.
Excellent. Great.
Yeah, I will try to keep an eye on the chat box, but sometimes if I'm sharing the screen, then
I know. I'll keep an eye out for you. Okay.
Yeah, it has been 1 year, so everybody knows that how Zoom works. Okay, so let me start. And if you guys already know about those the basics, then I will try to go faster on this part. Otherwise, I will try to have some details here as well. Okay. So let me start with the first neural network architecture, which is called a fully feed-forward, fully connected neural networks. So mathematically, we first introduce the layer for those FNNs for the feed-forward neural networks. So this is simply a mapping from some input, which is from D1, for example, to some output, which is in RD2. And then the transformation is simply you do a fine linear transformation and then plug it into some function that is so-called activation function. So if we write it in the matrix form, here, this is the definition for the a layer in the fully feed-forward neural network. Then we have this output to be given by a activation function applied elementary wise to the affine transformation of the input. Okay. Where W is the collection of all the Wij's, which is the weight, what we call the weight in the neural network, and then the beta or B is the bias. Okay. So those W and beta, those are the parameters of these neural networks, which later on you want to find a optimal ones using your training data. And we will talk about how to optimize those things in a second. So W is called the weights here. And then beta is called the bias. Okay, and for each layer, they are associated with, usually they are associated with different weights and bias. So therefore, if you have a fully connected neural network with different layers, then you are actually composing all those activation function and then the transformation. Okay, before talking about the full architecture, let me also mention when we when we choose the activation functions, there are several criteria. For example, it depends on what problems that you are working with. If you are doing like a classification problem, like in the traditional computer science, the inputs are some images. And then the outputs are some the truth of the picture, whether it's a dog or it's a cat, or whether this handwritten digits is a 1 or is 9. Then people usually use the sigmoid functions. Okay, so this is the sigmoid function. Or if you are doing some problem where you require your output to be like positive, then people tend to use the ReLU function. This is the ReLU function, which simply take the positive part of after you do the affine transformation. Okay, And then as long as we understand how the data are fed in one layer of the feed-forward neural network, we can have the notation for the whole feed-forward architecture. So this is simply to compose different layers, which we call from phi 0 to phi 1 until phi L, where L is the depth of the feed-forward neural network. Okay, and you need to have all the input dimension, output dimension to be compatible with each other. So therefore, if my the output for the first layer is D1, then the input for the second layer has also to be dimension RD1. Okay. And then if I want to express all the parameters into a feed-forward neural network with input activation with activation function rho and rho tilde, and also with the layer with L layer, and also with all the dimensions, then basically I'm collecting all those parameters here. Okay, so beta 0, W0, they corresponds to the weight and bias for the zeroth layer, and then the beta 1 and W1 are the parameters for the first hidden layer, blah, 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 until the last one is for the output layer. Okay. And if I use the vector and matrix notation and really spell out how data are fed from the input to the output, then it is the final expression. Okay, it's here. So this is the mathematical notation here, where this represents the first affine transformation, or after plugging, you have the row of this part. This is like the input output of the first hidden layer. And then you consider this as the input, and then plug it into the next layer, and then do the affine transformation, and again plug it into the activation function. And you keep doing that, and later, and then you will produce the output of the this neural network. So apparently, this is a function of your weight and bias, and in practice, your weight and bias, those B and those beta and Ws, there are many of them. So you have a very high dimensional function that maps your data to some output, and then those parameters are your choice of the W and beta. Okay. So this is one type of the neural networks people that are widely used in many areas, and mainly due to the ability as a function approximator. So we will see in a second for some universal approximation theory explicitly saying that those simple neural network, even with one hidden layer, but with many neurons in this hidden layer, that can approximate function as close as you wish, basically. Okay. And there's another type of neural networks that has been used in dealing with control problems, stochastic control problems, or even in particular with delay feature. And those are called the recurrent neural networks. So that's the second architecture I'm going to talk about today. Okay, so in the past, or it has shown its excellent performance in dealing with like a sequence of data when there are some path-dependent properties. The recurrent neural networks are usually tried and have better results compared to the feed-forward ones. And there are many variants for the recurrent neural networks, but basically, they all share the following the feature. So we will talk about the common ones first, and then go to the Lstm, which is the most popular one. Okay. So for the RNN, then there are like two types of inputs. There will be a sequence of data or a sequence of input, which is denoted by X here. And then you also need to give this network a initial state of your H that is denoted later on by H0. Okay, you will have X0 and 2XN, for example. And then with those two informations, you flow those into one cell, and then they will repeatedly produce the H1, H2, H3, and also the output, which we denoted by Y. Okay, so you plug in the input and then the previous and also the previous output for your H part that produce the new H, and then you get the output. So if you are already seen the recurrent neural network before, then you must have seen the following unfold architecture, which I will briefly repeat here. So for one cell in the recurrent neural network is actually you have a loop into your architecture. Okay. So your H is your like an inner state, and you have an output which we denoted by Y, and then you have the input which we denoted by X. Okay. So the data will be fed from X to the H, and then this will produce a new H as a new inner state. But then this information will fed again back to the cell, and with the new data together to produce the new inner state H. And meanwhile, for the previous inner state H, you will also do a fine transformation, plug it into activation function, and this will produce you some output Y, which is called Y here. Okay. So unlike the feed-forward neural network where there's no loop in the network, and the information is always fed forwardly and never fed backward, in this recurrent neural network, you explicitly have a loop like this. So the previous output of the neural network will be fed into itself again, and people has the interpretation that they are mimicking like the neurons which fires for some time before becoming quiet. Okay, and if I spell this out, if I do a unfold this architecture, then basically this is the flow of the information. So you have H0, and then you fed it to H1 together also with the information input X0. And here you are using a activation function rho, and this will produce a output Y1 and using the activation function rho 1. But the H1 information of H1 will be fed into the next, will be fed again back to this cell, and then together with X1 to produce the output Y2. Okay. And then you keep doing the flow. And maybe from the beginning, if you look at it, this looks like a very similar to the feed-forward neural network, but there's actually a difference because the parameters that you are using to go from H0 to H1 and from H1 to H2, they're the same. So they share the same set of the parameters. Okay. So what I'm saying is that the relation or the transformation when you go from for those red arrows are the same if you are going those if you are doing those green arrows. Okay, so we only have like one set of the parameters when we go from the input of H and X to the output H prime here, and we also only have one set of the parameters to produce from the inner state H to the output state Y. Okay. So to summarize, this is the how the recurrent neural network are producing the output Y, as well as determine their inner state state H. So as I mentioned before, you have your sequence of input data X. This could be like a time series of like a stock, or a sequence of a video, a sequence of like videos, or like some if they are doing natural language processing, then this could be some sentence, for example. And then Y is some particular like signal that people are trying to find. For example, if you are input a sequence of your stock data, then this Y might be the prediction whether for the next step is the price going to increase or decrease, or if you are putting into some sentences, the output may be some understanding of this paragraph or this sentence. Okay, but basically you are trying to use the current stage of your input plus the previous output of the inner state, and to produce the current state state of your inner state, and then to do a fine transformation, plug it into another activation function to get your output. Okay. So this is the most general architecture here, and then let's go to the LSTM. I think I'm maybe too slow here, and I will try to be faster. Yeah. So for the LSTM part, they have the so-called three gates. They have the input gates, output gates, and also the forward gate. Okay, for each of the cell. So they are the elements to control how the informations are flowed from time to time. So the input gates take care of how much of the information that will be received this round, and then forget gates will take care of how much of the information will be forgot from the history. So basically, for each of the gate, there is a fine transformation as before, and then that will be plugged into a activation function, which particularly the sigmoid function is used here. So let me remind, 0s is called the sigmoid function. Okay. And then this also applied to the input gates and then output gates. For each of them, you do a fine transformation with the current input data and then the previous states, and then plug it into the sigmoid function. And then the state of the cell is determined by the following way, and where this dots denote is the hand-marked product. So it's an elementary wise product between two vectors. Okay. And from the definition, you will see explicitly why we call this F to be the forget gate. So the forget gate controls how much of the information from the previous step is fed into the current one. And the input gate takes care of about how much the current information will be remembered into the current cell, and then with the cell, they produce the output of this unit, which is another time of the hand-marked product with the output gate. Okay, so that is pretty much about the neural network that will be used in the control and the games later on that we'll talk about. And then the next main objects in deep learning that is relevant is the stochastic gradient descent and its variance. So as we mentioned, the target here is you try to learn the optimal weight and bias from some sampling data or some existing data. So mathematically, we can summarize it into a generic optimization problem, which is a function of your high-dimensional neural network parameters. Okay, so mathematically, when doing the stochastic gradient descent for any loss function with a particular neural network architecture, but you are basically trying to minimize over this phi. So this is the like our neural network parameters. And then with respect to a set of random variables or a set of random processes, and under its expectation. Okay. And then the first step here is people usually try to approximate expectation by the sample Monte Carlo sample average. So this will rely on the empirical risk minimization problem. So you take a bunch of the samples from the distribution nu, and then you compute the loss function, and then you try to average them. Okay, and if you have a very, very large n, then you need to, though you have a good approximation for your expectation, but this will really slow down the efficiency when you are computing the gradient, right? So when you are trying to do the update your parameters theta, then for example, if you are doing the case iteration, usually people start from the theta 0. Oops, sorry. Okay. Then people update theta k from theta k plus 1 from theta k, but then minus a learning rate multiplied by the gradient of your empirical loss function, something like this. And if your n is really large, although you can have a good approximation of your original. It's 7 o'clock. I'm sorry, that's made by my computer. If you have a large n, then you can have a good approximation for your expectation. Therefore, you produce a good accurate gradient for your loss function. But this will really slow down the update, the computation for the gradient. You have accurate. Therefore, people try to do some compromise and then have a small random set of your samples, and then update your parameter theta, and that is called the mini batch stochastic gradient descent. Although nowadays people omit the mini batch and then simply jump to the stochastic gradient descent. But then slow. Okay, so this leads to the most well-known algorithm. Will try to minimize find the optimal parameters here, which I summarized in this algorithm 1. So basically, for a mini batch stochastic gradient descent, or nowadays people call it simply the stochastic gradient descent, they sample a mini batch of the C following this distribution nu, and then they compute simply the gradient of the loss function using this mini batch, and then they do the update. Okay, and here is the update scheme, where the beta is some parameters that are usually chosen by the user. So there's some philosophy behind how to choose the learning rates. People usually start by looking at the loss function, and then after some stages, they try to shrink the learning rates, and then to try to like do some minor adjustments. But then for the stochastic gradient descent, since every time they only use a mini batch of the samples, there could be a large variance about the gradients thing here. So then there are many variants of the SGD, and in particular one of them is called ADAM, which refers to the adaptive moments. Okay, so for the adaptive moments, although they are still using a mini batch of samples at each time, but then when they do the update, they will take into account the past information of the gradients. They will combine the previous gradients estimates into the current stage and then use them to do the updates. So what is the difference between the ADAM and the SGD? So for the previous vanilla SGD, when after computing the gradients, they simply use that to update the parameters for the particular iteration. But here, if you are doing the ADAM, then you first compute the gradient, which I need to do here, and then they use those information to update to obtain the first moment estimate of the gradient and the second moment estimate of the gradients, which are given here. So those are some formulas, and then they have explanations, derivations of those estimates in the original paper proposed by these authors. I think there are some people, those are people from Microsoft who proposed this, and then they do the update of the parameters in this way. Okay. Oops. Yes. Yeah. And of course, there are many others algorithm. And nowadays, if you are really into the coding part and for any deep learning packages, for example, for the PyTorch or TensorFlow, they already have those algorithm built in. So you simply input a command, one line of code, and then you can pick your favorite like algorithm. Okay. And then talking about those two main things in the deep learning, let me also mention why this is so popular in high dimensional problem. And there are some theoretical backup behind it, and this is called the universal approximation theory. So what that means, basically, for various types of architectures for various types of neural networks, people have shown that they have the ability to approximate like high dimensional functions or some dynamics. So let me briefly mention some work in the literature, mainly go back to the last century, starting from 1989 or 1990. People start to get interested in the explaining the universal approximation. Okay, so there are several types of universal approximation results. When in the past days, people are mainly focusing on shallow neural networks, and but with many neurons in this hidden layer, and that is starts by or maybe not starts by, but the celebrated work is by Hornick and his co-authors in 1989. So let me say for the shallow feed-forward neural network. Okay, and then there are several papers working in this direction, but the common the common message conveyed here is that a feed-forward neural network, okay, with a linear output layer and at least one hidden layer with any like the good activation function. I will explain what good means. So there are some requirements for the activation function for the hidden layer such that those approximation results hold. Okay. Okay, so those feed-forward neural network with one linear output layer and at least one hidden layer, they can approximate any Borel measurable function. And usually the approximation is constructed on a compact set. Of RD, where D is the dimensionality of your input. Okay. So there are several types of results along this direction. The first one that I want to mention is by Hornick and his co-authors, and also White, in their paper in 1989. And what they prove is that this good activation function, they call it to be the squashing function. Needs to have the following property. So they it needs to converge to 1 if x goes to plus infinity, and then it has to be 0 if x goes to minus infinity. So then apparently the sigmoid function is a valid choice here, right? The rho sigma, the rho s is a valid choice. And then later on, there are other people join this research direction. And then at the same year, they have the another one called Siboko, and then they also prove something similar, but using a different approach. For Hornick's work, they are using the Stone-Weierstrass theory to prove it, and the second one they are using the Han-Banach theory. So a different approach. And then later on, by Hornick himself, he proved that the feed-forward neural network with linear output and layer and at least one hidden layer can not only approximate the function itself, but also the derivative of the functions, if the activation function is smooth enough. Okay, and then also later on in 1993 by Lstm and his co-authors, they said as long as the activation function is not polynomial but of the sigmoidal type, then it can the neural network can be the universal approximator. So here the good activation function means it's sigmoidal. I mean, it's the same definition of the squashing function that is used in Hornick's paper. So you have the sigma of the plus infinity is 1, and then sigma of the minus infinity is 0, but you want it not to be polynomial. So as long as your activation function has satisfied those requirements, the neural network itself can serve as a universal approximator. So those are some results for the shallow feed-forward neural network, but later people also have results for recurrent neural networks. So recurrent neural networks are shown to can universal approximate dynamics. So this is by a paper by Schaeffer and his co-authors. This paper is about the recurrent neural network. So if you have a dynamics the main results is the following. You have the Rnn can approximate a dynamical system. If your system is of the following. Okay. And then there are also some proofs for the convolutional neural network, which was widely used in image processing. Okay, and for most of them, they are dealing with if you have a shallow neural network, but with infinitely many neurons for those hidden layer, then the approximation works. But along the other direction, nowadays with the powerful GPUs, people are trying to working with more deeper and deeper neural networks. And then the other direction is, what if I try to constrain the width of the neural network, and then I increase the depth of those things, and then can we also have the same like results? And then the answer is yes. So for the other type of the results, I would simply put some reference here. I think we already like spent like 45 minutes for the first part. So let me try to speed up. Okay. But for both of those papers, one is by Hanning in 2017, and then the second one is by Lu, Pu, Wang, Hu, and Wang in 2017 as well. Both of them try to say that with a fixed width of each hidden layer, if you have enough hidden layers, then you are also able to well approximate the function that you want to do. You want to approximate. And they particularly give some lower bounds of the fixed width of each hidden layer. And I believe they at least want D+3 or D+4 to be the width here. D+3 or D+4. In the two papers, they have different lower bounds for the width of each hidden layer, and where D is the dimension of the input, the dimension of your data. So therefore, I think those papers can serve as some guidelines for architecture design. So at least if you are dealing with a high dimensional problem, then do not have a really narrow neural layer for your architecture design. You want to have enough freedom so that you can have those theory work. I mean, theoretically, the thing can be a good approximator. Okay, so this is pretty much I want to talk about on the deep learning part. And Sebastian, do we have some break in between, or?
It's up to you if you feel energetic enough, or we could just take a 5-minute break to give everyone a chance to stand up, walk around, and
Sure.
start again.
Yeah, that would be nice.
Sounds good.
And then we switch to the next topic, which is
okay, great. Let's do that then. So we'll start back at 10:22.
Sure, yeah. So, thank you.
Zara, would you like to pause the recording and then restart it?
Thank you. Okay, so let's continue the second part, which is about stochastic control problems and how those are solved by deep learning. So first, let me give the problem formulation here. For stochastic control problem, you are basically having a stochastic differential equation of the control type. So you have this dxt equals to b dt plus sigma dwt, where w is your Brownian motion, b we call it to be the drift term, sigma is your volatility term, and x is the state process. And alpha is your control. It's something that the agent or the player wanna decide in order to maximize the reward or minimize the cost of herself or himself. And for example, the X we could think about is you have a wealth process. X is your wealth process, and alpha is your some of your trading strategies. And then you are trying to be happy through your investment period, or you want to be happy in the end. That corresponds to your running reward or terminal reward, or you do some consumption here. You do you are investing your money, but you are also spend some money on goods and then you want to have your utility maximized in the end. So those are like the problems in math finance considered, and that has been there exist for many years. And there's a whole a bunch of theory developed behind. Several approaches try to tackle those problems mathematically and giving the existence of the optimal control or uniqueness sometimes, and some characterizations of the optimal strategy process, or the minimize the cost or the maximal reward. All the characterizations are there developed, and then on the numerical side, usually with a realistic model or a high-dimensional model, then things becomes less developed before the development of the deep learning, before those powerful GPUs exist. Okay, so having said that, what I mean is, if you are given a stochastic differential equation, a stochastic control problem of dimension maybe more than 10, and you want to have some numerical approximations, and you have some sort of the constraints for your maximization problem or minimization problem, and they are usually not efficient numerical scheme here. Okay, and then people introduce deep learning to this area. Okay, and this is what I was trying to talk about in the second part of this tutorial. So let's go back to the formal definition. So here we would assume this X to be in the RD space, where D could be higher, like more than 10 or like 50, something like that. It's a high dimensional stochastic process, and then the B and the sigma and the Brownian motion are all high dimensional, and they are matrix and vectors, and they have the compatible dimensionality, which is given here. Okay, and the goal here is try to determine this optimal control alpha, such that such a expectation is minimized or maximized. And then the set of the strategies that we are searching within is called the admissible set of the strategies. Okay. So what we are doing is we try to do this minimization of alpha within this set A. And then usually there are two sets people are particularly interested. One is the progressively measurable processes. So FT here is the filtration generated by this Brownian motions, the natural filtration. Or people are more interested in the so-called Markovian strategies, where you have this alpha to be a measurable function of your time and your state process, the current state of your state process. And you also require this alpha as a process to be a square integrable. So those are some particular choices that I have seen in the deep learning applied to stochastic control problems. And then we will start with the Markovian case. Okay. So the second one is also called Markovian case. And then we will talk about mainly 3 different approaches to deal with for how deep learning is applied to this stochastic high-dimensional stochastic control problem. Okay. So the first type is called the direct primarization. This is simply to take advantage of the neural network's ability of efficiently representing high-dimensional functions without any spatial grace. Okay, and the idea here is we directly replaced the candidate control by a neural network with appropriate inputs. Okay, this is the whole idea here. And then the first paper along this direction is proposed by Han and Jiejun Han and Weinan in a NeuralIPS workshop like 5 or 6 years ago. That is what I remember. Okay. So what they do is they directly start considering a discretized version of the stochastic control problem we just seen, or we can think it in another way. We discretize this continuous version problem, and now we have a Euler. For example, we do the Euler discretization, then we have a discretized problem. So basically, you are facing such a optimization problem. And you want to do the minimization of the expectation of the Riemann sum of your running cost. Yes, yeah, I'm writing here. I'm sorry. Let me remove this part. Is the this is the discretized one. Okay, and then the idea is very straightforward. In the problem, they try to find optimal alpha, and now they are parameterizing those alphas using neural networks. Then the optimization with respect to the alpha will be transferred into the optimization with respect to the neural network parameters. Okay, so what they really propose is they simply replace the thing alpha ti, which they consider the Markovian case. And so those are the functions of the Brownian motions. I'm sorry, those are the functions of the t and the state, and they replace it using a neural network, which I express in this way. In particular, in their original work, they say for each for the control at each time, they use a neural network with a parameter theta I, but later on they also mention you can share the parameters of those neural networks by adding one more dimension, which is the time dimension. So you can also say you have one neural network which identified by alpha, but then the input will be ti and then the x part. Okay, and now you have simply one set of the parameter for all the for the control at each time step. Okay, so after replacing this candidate control by a neural network, then the problem, as I mentioned before, is translated into a machine learning problem where this is your loss function, or this is your cost function, and with a some parameters lying in the high dimensional space, the theta, and then you can use your stochastic gradient descent or its variant, your favorite one, try to get the optimized or near optimal parameter theta. Okay. And then here I'm using the notation x check theta ti to be the discretized version of your process when you are simulating your process using the neural network approximated control. So this is how the process is simulated forwardly. So this part serves as the data for the training of the neural network. So you sample lots of your Brownian motion, you simulate this x in a forward manner. Okay, and then you plug those into here to compute the loss for each sample, and you collect a mini batch, you do your gradient descent, stochastic gradient descent. Okay, good. So this is summarized here. Good. So the idea is that if we can find some near optimal theta such that this J check of theta is almost minimized, then we hope to say the optimal control is given by this neural network plugged in this parameter. Okay, so this is the whole philosophy here. And in their paper, they also explain how to deal with constraints. So for example, if we are thinking about the optimal the portfolio optimization problem, or the so-called optimal portfolio problem, then you also always require the wealth process to be non-active, right? Or sometimes you want your control to be within a certain domain. In that case, those constraints can also be taken care of by adding some penalty functions to the laws that we just defined. Okay, so for example, if in some of the applications you want some constraints, some bounding constraints or some unbounding constraints, then you can add penalties of the L2 type or using some ReLU functions. Okay, so for the constraints where you want those relations to be exactly zero, then you simply add the square of these terms. Therefore, that will try to push the relation back to zero. Otherwise, you will have a punishment right there, right? So you just add your j hat of theta to be j hat of theta plus the square of this term, basically. And if you want it to hold for every time, then you want to do a summation over all the time steps. Okay, and for the unbounded constraints, if you just want to require something to be non-active, for example, if you are dealing with the if your x is your Wells process, you simply want your x to be above zero. Therefore, you can take the negative part of it and then to do the ReLU. So therefore, it will punish the negative part of this relation. Okay. So you do the ReLU function of the negative part. And then, of course, you want to have some tuning parameters in front of those penalties so that you can balance the relation between this loss function and the penalty. Okay, so those are some fine tuning parameters which you need to do the trial and error, and then to see the magnitude of those quantities, and then try to have a balance. So far I haven't seen a universal rule which can easily define those parameters eta and eta tilde. Okay. Sure. Good. And there is actually another work by Pham and his co-authors, they also try to do the direct parameterization to solve stochastic control problem. Then, and what they do is they combine the dynamic programming with the direct approximation of the control and the value function, and try to solve the control problem backwardly. So they also start with a discretized version of the problem, and they say they know what is the optimal solution at time capital T, and then they work backward one step for the time T capital T minus 1. What is the optimal control there by using dynamic programming, and then they solve the problem backwardly. Okay, I think I won't be able to have enough time to cover everything here, so let me skip this part. But I will briefly comment the difference between these two algorithms. Okay, and for the second approach along this line, here is the reference. If you are interested, I think they have the papers posted on arXiv and also recently got published. Yeah. So the difference between these two is I clearly written here in the remark too. So for one, the first method I mentioned, this is one global minimization problem or optimization problem. You do one SGD, and then you determine all the parameters, you determine all the optimal controls at once, right? And then for the second one, where all those optimal control are learned sequentially and then the backwardly. Okay, and in the second work, they actually have a comparison with the work from Jiechun Han and Ruimeng. And what they comment is the first one, the global method, which what they referred may be efficient as in practice. The neural network for optimal control at each time are designed to share the same parameters, which I just also mentioned, they simply add one time dimension and then they share all the parameters and they can get trained at each time at the same time. But if you are having many small steps, this can result in the neural network to be really deep, and then you can have a vanishing gradient problem or exploding gradient problem as we are shrinking the time steps. But for the second work, which is combined with dynamic programming, then they are only dealing with one step for the optimization problem. So that it's less common to see the vanishing gradient in the second part. But for the second one, since it's not a global optimization for all the time, then you always having this propagation of the error. So maybe your first several steps are learned pretty well, but then the error are accumulated from time to time. Then back to time zero, it's hard to control the error at time zero. That is what I would say. Okay, and the after this direct parameterization problem, they are both working with the Markovian controls. So you might wonder if I'm dealing with just adaptive controls, is there any easier way to deal with the problem? The answer is yes. So in the Markovian control, you simply take the input of your neural networks to be your state process, the current state of your state process, and the time, right? So this is what you plugged into your neural network. And if you want to look for adaptive control, then by definition, this alpha t will simply be a function of the whole trajectory of the Brownian motion up to this current time, right? And in the discretized case, you can simply plug in all the Brownian motion, all the discretized Brownian motion up to time ti if you're approximating the control at time ti. So what I'm suggesting is that if you are doing the Markovian case, then for the direct parameterization approach, then you can do alpha tixt, and then with common shared parameters for each of the step. And then if you are just doing the adaptive control, okay. Then you can plug in all those Brownian motions for each of the steps, and then use the neural network to parameterize the adaptive control problem. Okay. And then immediate generalization for this direct parameterization approach is we can deal with the stochastic control problem with delay using the Lstm neural network. So this is actually my work, a work by my co-author and me. So we have this paper published in a special issue of the MCSS. So the problem, the contribution basically there is, if we are talking about the stochastic control problem with delay, which is described by a stochastic differential delay equation. Okay, here. And this is the objective. Then we can show that the Lstm, the long short I'm sorry, the Lstm neural network really can do better than the feed forward ones, where here I would the notation xt with the underline is the trajectory of this process on the interval from t minus delta to t. So the system now has a fixed delay. The dynamics at the current time of the state will depend on all the information up to t minus delta. Okay, and this also applies to the objective functional. So now you have the f and g to be functional of those segment of your process. Okay, and we are in this work they're like simply trying to compare the the two types of neural networks. So what is done there is they get some questions where you have the closed form solution. Okay, so they are directly jump to the I'm sorry. Sorry for the interruption.
Oh, okay. I was just going to say, it looks like we lost Ruimeng for a moment.
Yes, I just have my kid working around. Sorry about that. So for this problem, for this work dealing with stochastic control problem with delay, they jump directly to some examples, and in particular for the linear quadratic problem with delay, there is a closed form solution if the dependence is of a particular type. Okay. Good. So in this case, the dependence would be on the x itself, and also on y, where the y is the distributed delay. So they average the path for delta history, and then this will influence the dynamics of x. And they also have a discrete delay, which is simply the value of the most historical point xt minus delta. Okay, so they appears here and here. And by a particular relation between all the coefficients, it is able to derive some closed form solutions, which I give here below. Okay. And for the other parts, the A1, A2, A3, B is sigma, and they are both deterministic functions or constant matrices, and they need to satisfy this relation 13. Okay. And So this is the one of the example that they study on, and then let me show some numerics here. And they basically compare the two architectures. One is the feed-forward, and the other one is the LSTM. And then in terms of the training, in this particular example, it's not that obvious that LSTM can do much better than the feed-forward, but there are some incremental incremental advantage here. So the validation cost is actually the minimization cost that, oops, is it stuck here?
I see your mouse moving.
But can you see some pictures? No.
Oh, no. Right now I'm stuck on equation 12 with LQ and cases.
I see. Let me try to share again. Yeah, something. I hope it's not the problem of my. Okay.
Now we see figure 1. Yes.
Oh, okay, great. Thank you. Yeah, I just saw a comment in the chat, and then yeah. Okay, so this is a plot for the validation cost of the two architectures that we chose to do the comparison, and then the blue ones is the LSTM, and then the other one is the feed-forward, the green, the orange one. For this particular example, actually, we didn't see much improvement from the feed-forward, from the LSTM to the feed-forward, but you do see that the green line will give you a lower cost for this problem, and we know that we are minimizing things, so the lower the better, right? And it has also converged faster than the feed-forward. And there are other advantages for the LSTM. For example, in the reality, we may not be able to know the delta in priori. Okay. But delta is very important if we want to cooperate, if we want to use the feed-forward neural network, then we want to feed the whole past, the whole history into this network. Okay, and in order to feed the whole history or the discretized version of the whole history, we want to know exactly what delta is. And if we estimate the delta wrong, then we might not be able to have a good results. Okay. But for the LSTM, this is not the issue. The delta is figured by itself using those forget gates, and then input gates, output gates, especially the forget gates, right? Although for the whole cell, it has all the information from the very beginning to the current state, but then by the intrinsic forget gate inside of this LSTM, they will get rid of all the not unneeded the past, like during the training. Okay, so this is what this is the one advantage of the LSTM here. So basically, if you are doing the feed forward, then this will be a ATK equals to a feed forward neural network with the input XTK minus 1 until XTK minus some number L, and this as TK, where the delta T multiplied by L is all the delay. Okay, this is what we want to feed to the feed forward neural network, but in reality, delta may not be known. So you might feed a shorter length of your data into the neural network, or which of course will produce some suboptimal solutions, or you might just to play safe, you have a longer information fed to your neural network, and in this case, in principle, you are able to approximate the true optimal solution, but you lose some of your efficiency because you have more unneeded information that is fed. Okay, but for the LSTM, since the very beginning, what is the sequence that is fed to the LSTM is simply the xt0, xt1, until xt capital N. Okay, so at each iteration, you feed the cell this just this state for the current moment, and then the LSTM will automatically determine whether they want to remember this information or forget the information controlled by the forget gates. Okay, that is why I would say LSTM is more efficient in dealing with a problem with delay, and in particular that is supported by the our paper and with like 3 benchmark examples. Okay, I think I will stop the direct formulation here, but there's another application, or there's another work by René Carmona and Matthew Lauria. They also along this line of the approach, and then use direct primarization to deal with mean field control problem. Okay, so the reference is here. Okay, I can jump to the reference later on, the number 29. And what they basically do is they are trying to optimize a Volosov type stochastic differential equation, and this is what they want to minimize. And they are also particularly interested in the Markovian control, which is given here. And they also replace the control by or they will also parameterize the control by a neural network. And what they do additional here is they also need to do the approximation for the mean field. So here M is the distribution or the law of this X. So let me say that M is the law of XT. Okay, and then empirically or numerically, how this is approximated, and this is approximated by the empirical distribution. So what they do is they sample many paths here, and then they do the empirical average, and then to use it as the approximation for the real distribution. Okay. Okay, and then everything else is the same. It's very similar. So they first discretize the process, and then they replace the distribution by the empirical distribution, and then parameterize the control by neural networks, and then this is their like final version. The final version is here. The final version of their loss function. Okay. And in this work, they actually have some proofs, some theoretical guarantees for the convergence result subject to the universal approximation of neural networks. So suppose that the neural network can approximate the function that they want, then with sufficiently many training steps and many samples, the error would be proportional to the time steps and to the negative sum power of where n is the particles that approximate the distribution of the Markovian type. Okay. So I think I've said a lot for the direct primarization, and then now let's go to the next one, which is to solve the problem using the BSDs. Okay, so what we know is that when we are dealing with stochastic control problems, we can derive if the problem is in the Markovian sense, then usually people can derive the Ajb equations, and then or they can use the so-called stochastic maximum principle to get the forward-backward stochastic differential equations. Okay, so there are mainly two like reformulations of the stochastic control problems, and for each of them, we actually have the corresponding the machine learning tools or machine learning algorithm, deep learning algorithm to solve those problems. So let me start with the DeepBSD, and which is a application of the like nonlinear Feynman-Cake formula. So before that, let me write down the Ajb equation for our problem. So recall that if we have the stochastic control problem of the following type with the following notation, formulation, and then we have the running cost to be F, okay, and then terminal cost to be G, where F is also a function of Tx and alpha. I'm omitting here. Then we can define it, and if we are looking for alpha to be the Markovian control, then we have the following PD approach. So this V is now defined to be the suppose we are doing, okay, we are doing a minimization problem. Then the value function is defined to be the future cost if we start from time small t at the position x, the minimize the future cost. Okay, and then by dynamic programming principle, we can formally derive the Ajb equation. Okay, you can get the Ajb equation, which has the following form. Okay. Okay. And if we do have the control in the volatility part, then this will result in a fully nonlinear Ajb equation. However, in the special case, when we have the sigma to be free,
it's 8 o'clock
of the control, okay, then the Ajb equation becomes semi-linear. Okay. This is a semi-linear PDE. You can get this the trees of your sigma transpose, the Hessian matrix, to be out of your infimum, and then you can use the nonlinear, so-called nonlinear Feynman-Cake formula. Okay. Equals to 0. So in this case, your optimal the optimal control will be like explicitly depends on x and then the derivative of the function. Time and then the gradient. Okay. And then if you plug in this alpha into here, then you will see it's a semi-linear partial differential equation where you can use the so-called nonlinear Feynman-Cake formula. So in this case, if you have a semi-linear PDE, then by the nonlinear Feynman-Cake formula, you have a like a BSD representation. Okay. So let me give a little bit details here. I have like 30 minutes, right?
Yeah, just about 30 minutes.
Yeah, like less than 30 minutes. Okay. So if you plug in the optimal control here, then you will result in following semilinear partial differential, semilinear PD. And here, recall that we already assume sigma is free of the control. So this is by if you have the infimum of your Hamiltonian, or you have the infimum of this expression. And then you plug in, after you plug in the optimal control with alpha star equals to the admin plugin. Okay. So in the previous slide, we know that this alpha star would be a function of Tx and then the gradient. And then if you plug it in, then this will produce you another function, which is simply of the time x and also the gradient of the value function. So here, in order to apply this nonlinear Feynman-Cauchy formula, you need to assume that the infimum or the argmin here is unique. Okay, and then you will be able to get some semilinear PD. And then the next step is to say we assume this H function. It's able to be rewrite as the gradient of V multiplied by some function. And this mu function is served as the drift term of your forward process. So now you have a new forward process, which is the xt tilde. But the sigma will be the same as before. That the sigma is from your forward process, which you want to do the optimization. And then the backward process will give you the value of the value function and the gradient of the value function, if you can solve it. Okay. So the relation between this FBS, the BSD and the value function is the YT is particularly the value function evaluated at time t and xt tilde, and then ZT would be the sigma transpose of this. Okay, so now after this derivation, I've shown that if you have a simply linear control controlling drift problem or uncontrolled volatility problem, and you have a unique minimizer in your Hamiltonian, then if you can rewrite your H in the following sense, then you can translate the solution of your semilinear Hamilton-Jacobian-Bellman equation into the solution of your BSD. So having said that, that means you can try to solve the BSD instead of solving the Ajb equation. But well, of course, there's some machine learning techniques to solve the Ajb equation, which I will also talk in a few minutes. Okay, so I just want to show this derivation so that you can trust me. The uncontrolled volatility problem can be reduced or reformulated into a problem of solving BSDs. Okay. Okay, and then to fully express this approach, we will just use a generic BSD here. Okay. So B here is the drift of this forward process, and then F is the driver of the backward, and then both Y and Z serves as the solution for the backward part, right? And then the idea is still you try to approximate what you want by a feed-forward neural network. And in particular, here to solve the BSD, they use the variational form. That means they try to minimize over the initial position. So I'm going to circle them in red, which are approximate by neural network. Okay, so they try to guess, or they try to minimize over the initial position and the drawing process Z, such that the true terminal condition, which is given here, the distance between the true terminal condition and what's the result after the guess is close to each other. Okay, so this is the truth. And this is from the simulation. Okay. So basically what they do is they will introduce the direct parameterization here to replace the Z process by a neural network. And also they replace the initial position of Y using another neural network here. In that case, since you have the candidate for your drawing process, you have the candidate for your initial position, then you can simulate the Y process also forward in a forward manner. Okay, after you simulate both X and Y in a forward manner, then you have the your values for your G and for your Y, and then you compute the distance, the difference, and you will try to minimize the distance here. Okay, so the closer the better. That means if your simulated terminal condition coincides with your with the true terminal condition, then we think we got a solution for the BSD part. And then the samples that we need to use here are simply the you get the Brownian motions and some random initial positions of your forward process. Okay, and in the particular interpretation where we try to rewrite the solution of a drift control only problem into the BSD, then this B corresponds to the mu that we just defined in the previous derivation, and this F corresponds to the H that I just write. Okay, like if we have it here. Okay. So this one. But in general, you can deal with any type of the BSD, solving any type of the BSD using this BSD approach. And not only the BSD that are associated to the semi-linear Ajb equation. Yeah, that is what I want to also mention here. And the other approach that people have been using for a stochastic control problem is to directly solve the Ajb equation, and that is called, well, the one that first shown in the financial math group is called the deep Galerkin method that was proposed by Justin Signano and his co-author in Boston University. Let me go to there. Okay, let me skip this part, and then there's the PD-based algorithm. Okay, and this is the called the deep Galerkin method. So for the deep Galerkin method, what they do is they use the neural network to approximate the value function itself. Okay, and then they use the auto differentiation that is built into the PyTorch or TensorFlow to get the first derivative of those value functions. Okay, to get a gradient of Tx. But when they are dealing with the second derivative or the Hessian matrix, they use some stochastic approximations. For the, okay. And this is the particular reason here is the computational efficiency. So imagine that if your X is very high dimensional, for example, in our notation, we have X to be the RD. And then for the first derivative, you will have a vector which is d by 1, right? But if you are for the second derivative, then there will be a d by d matrix. Okay. And then imagine that you have many samples, then it's very computationally expensive to evaluate all the derivatives. And what they do is that they introduce some, they try to simulate some Brownian motions as the stochastic factor there, and then they can approximate those second derivatives nicely, efficiently. And then what they try to train is that they plug in, they replace all they replace all the functions, the derivatives by their neural network counterparts, and then they try to force the parameter such that the PDE relation is satisfied. Okay, that is the philosophy for the deep Galerkin method. Okay, so for example, they actually can do any type of the partial differential equation. So let me go here, the deep Galerkin method. But I will also briefly mention the concern of this this approach. Okay. So they can deal with any type of they claim they can deal with any type of the differential equations, linear, nonlinear, parabolic, elliptic, or hyperbolic, as long as and they can be expressed with the following. There's a PD relation, and then there could be an initial condition for X on the domain. So this is the initial. And they can also have, it can also deal with the a boundary condition. And as I mentioned, the value function itself is approximated by the neural network. With some parameter t, with some parameter theta, and then the gradient is by the auto differentiation. It's given by the auto differentiation of this neural network. And then the second derivative is approximated by the using some stochastic approximation. So basically, they simulate several Brownian motions, and they if the second derivative is defined in the following way. Then this is approximated by the following. Some derivative, and then this is the delta. And then you simulate the Brownian motion W delta. with the parameter 0 and delta. Okay. Yeah, there's some difference here. The first derivative evaluated at some points. Okay. So let me omit this part. And then what they do is they plug in those approximated terms into the three equations above. So they replace all the things by the right-hand side and then plug replace all those things by the right-hand side. And then the loss will be the difference, how far away the truth is from the right-hand side of the equation. So what they do is they have the loss, the partial neural network, partial T minus the L of neural network. So this will take care of the PD relation. And then here we'll take care of the initial position. And then the next term will take care of the boundary condition. Okay. And then for sum of the x and t. So the problem here is that I will try to maybe stop after 5 minutes. The problem here is that first, how to do the samples of your T and X. So what is your domain of interest? In many of the financial math problem, you have an unbounded domain or you have a unknown boundary. For example, if you are dealing with American options, then you do not exactly know what is your partial of omega, right? So this is determined by your immediate reward and then the cost to go. Okay, so you do not know what exactly the boundary, then how would you sample your T and X along the boundary? That is a problem. And then for some of the problem, you have a unbounded domain. For example, if you have the Morton problem, the portfolio optimization. Okay, and then omega is unbounded. So we know that how to sample points on a bounded domain. There are many ways to do it, but for unbounded domain, then how large we want to cover, or what is the large arm you want to choose to approximate this unbounded domain. So those are some questions that people need to think about. Yeah, but in their work, they also have some theoretical guarantees. That is good because not all the right now, not all the deep learning algorithm can have the those theoretical backup there. So I think I'm almost running out of time here. Let me, although I want to cover more in this tutorial. Right now, we basically finished the deep learning tools and then the basic 3 approaches for the stochastic control problem. So we talk about direct primarization, we talk about the BSD based algorithm, and we also talk about the PD based algorithm. And unfortunately, I don't think we have time to talk about the stochastic control differential games, where you have the unplayer games or the mean field games. There are many ways to incorporate deep learning techniques into those interesting games. But I want to use maybe like 2 or 3 minutes to mention like what I think are the interesting like perspective for maybe future research, or what I feel where I feel there could be more work to be done. The first thing that always I'm thinking is the accuracy results. So for some of the work that I mentioned here, there's no like theoretical guarantees, and then even with the theoretical guarantees, there are usually people try to assume the neural network has a universal approximation properties, and by assuming the solution itself a priori have some nice properties, so that works. So in this direction, I always feel that there are many things could be done. And then the second thing is that how do people really design the architecture of the neural network? So although in the first part, when we talk about universal approximation, there are some guidelines to say you cannot restrict the width of your neural network to be too narrow in order to have a good approximation in high dimension. There are more guidance around this direction. And then the second thing is, how would you really choose the hyperparameters? It is not clear at the moment, like for your learning parameters or really the depth of your network, the activation functions. People usually do this trial and error, and then they have some benchmark problems. They can do the comparison. But for real problems, which is also another interesting point that I think they deserve more attention. When there's no benchmark solution or a closed form solution, what is the good indication or good criteria to determine those hyperparameters? And then the last one that I would say is to use it to solve some real world problems. Okay. Yeah. Okay. I think I want to stop here, and hopefully I didn't get all of you lost in the end. Yeah, thank you.
Great, thank you very much, Ruimeng. That was, I'm sure, a whirlwind tour for some of the students that are in the room, and but it was great overview of a lot of interesting aspects of deep learning and stochastic control. I didn't see any questions coming up in the chat. There was one about references. For the two basic methods for applying to the control problem. I think I got them right. I put in the links into the chat, but we can maybe post those. I guess they'll be part of your slides. But since we do have a few minutes, does anyone have any questions they'd like to ask Ruimeng? You can either, I guess, given that we're at the end of the talk, you can just even unmute yourself and turn on your camera and ask away.
I think the references are correct for the direct parameterization. Yeah, thank you, Sebastian, for providing.
Okay. So I guess while we're waiting for the audience, so maybe I can ask something about your delayed stochastic delayed control problem, or delayed stochastic control problem. I don't know which order it goes in. Do I delay it or do I put it in the front? So
stochastic differential delayed equation, or stochastic problem control with delay. Yeah.
Right. Okay. So you looked at you had this comparison of whether the feed forward and the LSTM, which one kind of performed better than the other, and it looks as if there wasn't really much gained, I guess, right, by using the LSTM. It was a little bit improved. I think. Yeah.
Yes. This is because the particular example that I showed. The improvement is not that much. Yeah, so there are other examples. Let me see if I can show here. Let me try to stop sharing this one. Give me 1 second. And this one. Yeah, can you see the screen here?
Yes, I can see.
Okay, great. Yeah. So the example that I show in just was the first one where you have the linear quadratic problem with delay. But I mean, for other problems, we do see like a different more improvement here. Let me see. In particular, in the one that we have the complete memory. So in the last example that in our paper, we take this delta to be actually infinity. Like, so your trajectory depends on the whole path of your previous days.
Is it an exponential decay in the past, or is it what sort of decay?
It's an exponential decay, yeah, average.
Okay.
Yeah.
Okay. Right.
So
I'm sure if you had some sort of like power law decay, then it's probably going to be even more significant than this. I see. Okay, so there is a big improvement here.
Yes.
Did you try like GRUs as an alternate as well, or anything?
Yes.
Like this?
Yeah, I think so. They basically share the same like properties, and then we simply choose one architecture here, which is the LSTM. Yeah. They share very similar results. So we just take one for presentation purpose here.
I see. Okay. Cool. Great. Other questions from others in the audience? Okay, Alan Yang, would you like to ask your question? You can unmute and turn on your video if you like, or just unmute, or I can ask it yourself as well. Okay, I guess he's preferring that I ask. So I'll say, can you talk more about tuning factors? So I presume what you mean, Alan, is hyperparameters, or do you mean something else?
Like which part of the tuning parameters, the learning rates, or like the width or depth of the network?
I mean, it's unclear.
Okay, cool.
So pick the one that you want to answer.
Okay. So let me start with the simple one, the width and then the depth. So by some universal approximation theory that I mentioned in the first part, then we know there's some lower bounds for the width, right? If you want to approximate the function well, then you want the width to be at least 3 or 4 more than the dimension of your input. And usually, if you start designing, for me, if I start designing my neural network, I would have like 1 or 2 hidden layers, and that is also like has some theoretical guarantees. Or if you look at this paper by Haney in 2017, then they had a lower bound for the depth of the neural network. I mean, the upper bound of the neural network. So if the width is, so in principle or in theory, if you have the width to be d+3, then the depth is less than or equal to 2 multiplied by d.
I don't see, by the way, I don't know, Ruimeng, are you meant to be sharing what you're writing?
Yes, yeah. Thanks for reminding me. Yeah, I was sharing another thing. Yeah. Okay, so let me do the sharing of my. Okay, can you see right now?
Yes.
Okay, great. Okay, so what I want to mention, the first thing is by some already developed theory on universal approximation. In particular, in this paper, Haney in 2017, they gave a proof that if you construct your neural network with the width of d+3, then with a depth at most 2 multiplied by d factorial divided by the modulus of continuity to the power d, then you are able to approximate any function as close as you wish. Then this WF of epsilon is the so-called modulus of continuity of your function. So you want, that depends on how smooth your function is. X minus 1 less than x epsilon. Okay, so I hope this could serve as some guidelines on how you design this neural network with a certain width or a certain depth. Okay, and for another set of the hyperparameters, for example, the learning rates, then is usually by like trial and error. So at least for me, let me see. Here, those beta, I usually take them to be slightly decreasing. And at the beginning, I have maybe 10 to the negative 3 or 5, depending on the magnitude of the gradient. So sometimes I will plot the gradient of the problem for some initial periods first, and then to see to which magnitude those values are, and then to adjust my learning rates. That's my suggestion. And also, sometimes I would plot the loss across each episode, and then to see if there's no trend to decrease anymore, then I would try to shrink my learning rates. Yeah, so you are always trying to do some online adjustments, yeah, as time goes by. Yeah, that would be my answer.
Okay, great. Okay, well, I didn't see any other questions coming in through, but thank you very much, Ruimeng, for a really interesting overview, and still tons of work to do in this area. So there's lots of things open, and we now have a break scheduled. So,